Dear students, today we will be dealing with induction motor starters. In the case of induction motor starters, the functions are to reduce the starting current, and there are some protective mechanisms against overload and under voltage. And if it is the case of slip ring induction motor, the starting method will be improving the starting torque too. So the starters can be of two types or can be divided into two categories, where it will be applying a reduced voltage for starting as well as accelerating. This type of starters can be used for squirrel cage induction motor as well as slip ring induction motor. And second category, we can add additional resistances on the rotor circuit. That is possible in the case of slip ring induction motor alone, which can even improve the starting torque. For the analysis of the starters, we will have to keep in mind the basic equation for the torque developed. That is, Td is equal to Ks E2 square R2 divided by R2 square plus Sx2 the whole square. Or we can write the same equation as K1S V1 square R2 divided by R2 square plus Sx2 the whole square. We can write Td is proportional to V1 square, that is, the developed torque is proportional to the square of the supply voltage. It is clear from the proportionality, that is Td is proportional to V1 square, that if you are able to apply the full voltage on the stator winding, we can improve the starting torque. There are different methods that are used for starting three-phase induction motor. If it is the case of squirrel cage induction motor, we can go for direct online starting, stator resistance starting. And for both squirrel cage induction motor and slip ring induction motor, it can be auto transformer starting or star delta starting. In the case of slip ring induction motor alone, we can go for rotor resistance starting. We will see what is meant by direct online starting or DOL starter. Here we will be applying the entire voltage or the rated voltage itself to the machine. There are no control mechanism in the case of DOL starter, but there will be some protective mechanisms, that is for overload and under voltage. And this starter can be used only for a machine which is having small capacity, maybe up to 5 HP. Here is a diagram for DOL starter. OLRC implies overload release coil. UVRC implies under voltage release coil. NO means normally open, NC means normally closed. When the start button, that is S1, is pressed, there will be a current that is flowing through S4, S3, S2, S1 and through UVRC. When the release coil, that is UVRC, is activated, it will close the switches M1, M2, M3 and A. And the entire voltage will be applied across the stator terminals of the three-phase motor. When start button is released, the circuit will be closed through A, and if there is any overload, OLRC coil will be activated and will open up S4. It will be deactivating UVRC. Even if the stop button is pressed, it also will be acting in the same way, which will deactivate UVRC and will result in opening M1, M2, M3 and A. This is how the DOL starter works. There is no control for the voltage that is applied, but we have some protective mechanism of under voltage and overload. Hope you remember the equations. VAR is equal to 2 pi ns Td divided by 60 is equal to omega s Td, that is the rotor input power or the air gap power. And the rotor copper loss is given by WCU2 equal to 3I2 square R2. We have the equation rotor copper loss is equal to S times the input power to the rotor, that is SPIR is equal to WCU2. And we can find that the developed torque Td is proportional to I2 square divided by S. And since I1 is proportional to I2, we can write it as Td is proportional to I1 square divided by S. At starting condition, S is equal to 1 since the rotor is at standstill condition. So we can write TDS, the developed torque at the starting, is proportional to I1 square, or we can write it as TDS is proportional to ISS square. That is, the developed torque at starting condition is proportional to the square of the stator current. We will consider the running condition, that is at full load condition, TFL is equal to IFL square divided by SFL. SFL is the slip at full load condition and IFL is the full load current. And we can find the ratio of TDS and TFL, that is equal to IS divided by IFL the whole square into SFL. The starting current can be equated to IBN, that is the block rotor current at the rated voltage that is applied. So we can find TDSD divided by IFL is equal to IBN divided by IFL the whole square into SFL. For the analysis of the other starters, we will be keeping this equation as a basis, or we will be finding how much more or less torque will be produced in the other cases compared to DOL starter. So remember the equation TDSD divided by TFL is equal to IBN divided by IFL the whole square into SFL. Here we will consider an example where IBN or the starting current in DOL starter or direct online starter will be 7 times that of the full load current. If you are directly applying the entire voltage across the stator of a 3-phase induction motor, the current will be 6 to 7 times that of the full load current, and the corresponding full load slip is equal to 0.04, slip which is very small. By solving the equation we get TDSD is equal to 1.96 TFL. Here we can see if we go for DOL starter, it will be causing very high current, around 7 times that of the full load current, and it will be producing only 1.96 times that of the full load torque. There is a low starting torque condition in the case of DOL starter. Second type of starter is stator resistance starter. Here we will be adding a 3-phase variable resistance along with the stator circuit, by which we will be able to apply a reduced voltage across the stator terminals. That will help to provide a smooth acceleration for the machine. Once the machine picks up speed, we can cut off the resistance in steps. Finally, it will be short circuited, that is, there will not be any additional resistance on the stator circuit for normal operating condition. Here we have the circuit for a stator resistance starter. There is a 3-phase variable resistance. The supply voltage is VSL. By using the stator resistance starter, we will be applying only X times that of VSL across the stator terminals for the starting condition, and because of the same, the starting current will be reduced by the term X. So we can consider IS is equal to X times IBN. By substituting the equation ISN is equal to X times IBN, we will get the ratio of the torques as TDSR divided by TFL is equal to x square into IBN divided by IFL the whole square SFL. And we can find that TDSR is equal to x square times TDSD. That is, the torque that is produced at starting in the case of stator resistance starter will be x square times that of the starting torque that we had in the case of DOL starter. Here we can see the starting current is reduced by x times and the starting torque is reduced by x square times. In next type of starter, that is auto transformer starter, we will be applying a reduced voltage and by which we can limit the starting current. And here we will be using a fixed tap auto transformer. It can be used for both squirrel cage as well as slip ring induction motor. Here we have the circuit diagram for the auto transformer starter. We have a set of lower fixed contact as well as top fixed contacts. It is numbered from 1 to 6 at the top and the bottom. There is a moving contact mechanism too. There are two positions, that is start and run condition. At the start condition, the moving contact will be closing the lower fixed contacts, by which the supply to the stator terminals of the machine will be provided through the auto transformer. Once the machine picks up speed, the switch can be turned from start condition to run condition, where the entire voltage will be applied across the stator terminals. There are protective mechanisms for under voltage and overload. At under voltage condition, at run position, by using the relay coil, it will open up the switch, and for overload condition, the relay coil will be opening or it will be activating the relay coil and will open the switch S1, or the machine can be switched off by using the stop switch S22. We will now analyze the auto transformer starter. The transformation ratio of the auto transformer be K. So we have V1L is equal to K VSL. VSL is the normal supply voltage and V1L is a supply voltage that is given through the auto transformer to the stator terminals of the three-phase induction motor at starting. Since the supply voltage is reduced by K times, or it is K VSL for the induction motor, the starting current ISS will be equal to K IBN. But we can find the supply line current will be K square times IBNL by applying the transformation ratio for the auto transformer. So we have the starting current for the machine is equal to K times IBN, and applying the same in the equation for the torque, we get TDSA divided by IFL is equal to K square into IBN divided by IFL the whole square SFL. Here by using auto transformer starter, the starting line current will be reduced by K square times as that of the normal starting current, and the starting current for the motor will be reduced by K times, and the torque will be getting reduced by K square times. Next we have the star delta starter. The star delta starter can be used for a three-phase induction motor, which is normally designed for running with a delta connected stator winding. At the time of starting, the machine will be connected in star for the stator, and later it will be converted to a delta connected system. When it is started, since it is at star connected condition, it will be applying 1 by root 3 times the normal voltage, and later it will be the normal voltage that is applied. This can be used for both squirrel cage and slip ring induction motor. Here we have the diagram given for star delta starter. It is almost same as that of auto transformer starter. By the arrangement given, at star condition, the stator winding will be connected in star, and for running condition, the stator winding will be connected in delta. Along with the starter, we have the protective mechanisms for under voltage and overload. For the starting condition, since the supply voltage is reduced by root 3 times, the current also will be reduced by root 3 times. So the starting current will be ISS is equal to IBN divided by root 3. Since it is star, the line current also will be the same, IBN divided by root 3. For running condition, it will be converted or it will be changed to delta connection, and because of the same, the current that is passing through will be IBN per phase, and the line current will be root 3 IBN since it is delta connected. So the ratio of ILS divided by ILD we can find as 1 by 3. That is ILS is equal to 1 by 3 ILD. By substituting ISS is equal to IBN divided by root 3, we have IDSS divided by IFL is equal to 1 by 3 IBN divided by IFL the whole square into SFL. That is, the starting torque will be reduced by 1 by 3 times when we compare the same with the DOL starter. So the starting current is reduced by 1 by 3 times, and the starting torque is reduced by 1 by 3 times in the case of star delta starter compared to the DOL starter. If we compare the star delta starter with the fixed tap auto transformer starter, if K is equal to 1 by 3, both are having the same effect. Now we will consider the slip ring induction motor. For slip ring induction motor, we have slip rings connected with the rotor circuit, and we can have a variable resistance system on the rotor circuit. Till now we were considering a lower voltage applied for the starting of induction machine to the stator terminals, which reduces the starting torque too. Here in slip ring induction motor with starting resistances, we can apply the rated voltage itself at the starting condition, and for starting there will be resistances added to the rotor circuit, and these resistances will be gradually cut off as the machine picks up speed, and these resistances will be helping to improve the starting torque and to reduce the starting current. Here we have the circuit for rotor resistance starter. The stator control unit is same as that of DOL starter, but we have on the rotor side a variable resistance unit. After starting with the stator circuit, we can control the rotor resistance to adjust the current and the torque of the machine. The advantage in the case of rotor resistance starter is, for starting, we can apply the rated voltage itself across the stator terminal, and by adding an external resistance across the rotor circuit, we will be able to reduce the starting current and will help to improve the starting power factor and the starting torque. We have the equation TDST, that is the starting torque developed will be proportional to phi I2 cos phi 2, where phi is the flux and cos phi 2 will be the power factor on the rotor circuit. We have the equation for cos phi 2 is equal to R2 divided by R2 plus jx2, and the rotor current I2 is equal to E2 divided by R2 plus jx2. At starting condition, when S is equal to 1, the power factor will be much improved compared to the lowering of the secondary current, and because of the same, the starting torque TDST also will be increased. We will consider the design of rotor resistance for a single phase. Let the resistance of the rotor be R2 and X2 be the reactance of the rotor circuit. Consider the diagram where we have R1, R2, R3, etc. Rn-1 be the different resistances that are added in each step, and the total resistances be R1 dash, R2 dash, R3 dash, etc. Rn-1 dash and Rn per phase, and the corresponding studs be first, second, third, etc. n-1 and an nth. In designing the rotor resistance, we consider an upper limit and lower limit for the current. The upper limit is to limit the current, and the lower limit is to make sure that required starting torque is available for the machine. So when the rotor resistance is cut out, we make sure that the current is limited or is varied between I2 min and I2 max. That is shown in the diagram or the graph. You may also refer the diagram that is given in the previous slide with different studs and different resistances. At starting, the movable handle is at stud 1, where the rotor circuit resistance will be R1 dash. When the supply is switched on, the rotor current will be shooting up to I2 max, and the equation can be given as I2 max is equal to E2 divided by R1 dash divided by S1 plus JX2. S1 is the corresponding slip. When the handle remains at stud 1, the current will be reduced to I2 min as the machine picks up speed, and the slip will be falling from S1 to S2. We can write the equation for I2 min. I2 min is equal to E2 divided by R1 dash divided by S2 plus JX2. The difference in I2 min and I2 max is in the slip S1 and S2. Once the current is reduced to I2 min, the movable arm can be moved from stud 1 to stud 2, by which a resistance small r1 will be cut off from the circuit. During the movement from stud 1 to stud 2, the speed is considered to be remaining constant, and the movement from one stud to the other is called notching. Now at stud 2, we can write the equation I2 max is equal to E2 divided by R2 dash divided by S2 plus JX2, and the handle will be remaining at stud 2 till when the current is minimized, that is to I2 min, and we can write the equation for I2 min as I2 min is equal to E2 divided by R2 dash divided by S3 plus JX3. The difference is in S2 and S3 comparing I2 max and I2 min. The resistance remains the same because the handle is at stud 2 itself. Similarly, we can write the equation for I2 max and I2 min at stud 3. Here the change will be in the resistance as well as in the speed. From the equations for I2 max, we can equate those equations at stud 1, 2 and 3. Similarly, for I2 max also, we can equate the equations for I2 max for stud 1, stud 2 and stud 3, and we can generalize R1 dash divided by S1 is equal to R2 dash divided by S2 is equal to R3 dash divided by S3 is equal to etc. is equal to Rn-1 dash divided by Sn-1 is equal to Rn dash divided by Sn. And also we have R1 dash divided by S2 is equal to R2 dash divided by S3 is equal to R3 dash divided by S4 is equal to etc. is equal to Rn minus 1 dash divided by Sn. By combining the equations 3 and 4, we get the equation 5. And from the equation 5, we can write Sn divided by S1 is equal to Rn dash divided by R1 dash. Or we can write Sn divided by S1 is equal to R2 divided by R1 dash, where R2 is the actual resistance per phase for the rotor winding. And considering S1, that is a starting slip equal to 1, R1 dash is equal to R2 divided by Sn. And we can conclude the same as R2 is equal to K raised to n minus 1 R2 divided by Sn, or we can write this K is equal to Sn the whole raised to 1 divided by n minus 1. And thus we can find out the resistances that are connected on different studs as R1 equal to R1 dash into 1 minus K, R2 equal to K R1 dash into 1 minus K or K R1, R3 is equal to K square R1 dash into 1 minus K or equal to K square R1 etc. Here in the design, if the starting current is made same as that of the full load current, we can consider Sn is equal to Sfl. If the starting current is a different one other than the full load current, we will have to calculate for Sn. And for the design, we have not considered the leakage impedance as well as the no load current. And if we consider, we will have to consider the stator current also will be varying from a maximum value and a minimum value. For the design of the rotor resistance, for rotor resistance starting in the case of a slip ring induction motor, we can compare the same with the DC motor starter we had, and the stages by which we consider each resistance sections will be cut off in the starting mechanism, and the entire resistance will be cut out once the machine is running at the rated speed or when it reaches the rated speed. So in this section we are discussing on different starting mechanisms which will be helping to improve the starting torque as well as to reduce the resistance. And for all the starters there will be some mechanism of protection, that is the protection against the overload and under voltage. Hope you have understood the starters and the purpose of the starters. Thank you.